chapter 4.3. We're not going to get this finished today, so I've removed it from the homework that's due this week. So the only things that you need to worry about are the other two sections, 4.1 and 4.2. Right, so this will be part of next week's. So what we're going to look at is increasing and decreasing. Let's do that first. So we've got a function f of x, and we want to know the values of x where it's increasing and decreasing. How do we actually, find the intervals where it's happening? It's quite a lot of work in it. First thing we're going to do is remind you that when a derivative is greater than 0, a function is increasing. And for the values of x when the derivative is less than 0, the function is decreasing. Right? That's going to be important later. Can you remember how that works? If the curve's going up the way, we want the derivative be positive, and if it's coming down the way, we want the derivative be negative. Right? And we are going to use that. Essentially, you're going to get a function. I'm going to pick one right now and do it on it. So here's a cubic function. And it's 2x cubed, take away 21x squared, add 72x, take away 5. And this is a version equation 5. And for this function, we are going to find the intervals in which this function is increasing and the intervals on where it's decreasing, right? And let's put you through the steps. I've got it here first. The first thing you're going to do in any of these questions is that you're going to find the derivative and use it to find the critical numbers. So let's try that out over here. That's my step 1. Not the most difficult function in the world to differentiate. It's really just a whole of the power rules. Multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. You got that. And to find the critical numbers, in this case here, would you agree that the critical numbers are when the derivative is 0? So we're going to look for values of x that solve this equation. Very often there's 1, 2, there might even be 3 sometimes where that happens. And this is pure algebra now. Now, when I look at a guy like this and I'm saying, okay, I want to know when it's 0. My job should be to try and make it as easy as possible to solve. If I left it like this, that would be a horrendous thing to factor. Can anybody see what I can do to both sides, what I can divide both sides by to make this a little bit easier?
Getting 6 out of there.
Right, so you can pull it out as a common factor, or you can divide both sides by 6. And what's this going to be? 12. Are we comfortable with that? Pulling out a 6? Now, do you notice that this quadratic is much, much easier to do than that quadratic? And by that, I mean factoring. So, any volunteers for what this quadratic becomes when you factor it?
X minus 4, x minus 3.
Agreed. And that leads us to 2 critical numbers. One of them is at x equals 3, and the other one is at x equals 4. Critical numbers, places where the derivative is 0 in this case, they're going to be the points where an increase turns into a decrease, or a decrease turns into an increase. Something's going to change very often at these places. And that's step 1. Step 2 is create what I call a table of signs. And this is where it gets a bit messy. This is what a table of signs kind of looks like. Hope I put enough verticals, so I might need one more. Here, you put x. Here, you put the derivative of x. And here, you put the sign. Right, I have 3 and 4. Right, so you have a space here, you put a 3, you have a space here, you put a 4. So space, critical number, space, next critical number, space, next critical number, until you've done all the critical numbers, right? So that's why I put these in order. Now here and here, we put values of x that are less than 3. So any number will do. I'm going to put in 2.5 because I want to. Between here and here, I'm going to put 3.5. And over here, let's just be different, 5. So I'll put little green circles around these guys. These guys are variable. You can put 2.9 here, you can put 2 here. This number in the middle, right, this guy here, you're picking a guy somewhere between 3 and 4. I picked 3.5 because I like 3.5. You are allowed to pick 3.2, 3.9, as long as it's between here and here. And the guy at the end, you can put 5 or 5.1 or 22. Are you comfortable at how to create this piece of the table, right? You've got 2 critical numbers, 3 and 4, and you add a few more values of x based on that. Then you go to your calculator, and we are going to find out what the value of the derivative at each of these critical numbers. Well, actually, I don't need to do the critical numbers. Would you agree those answers are 0? We already know that that's going to be 0. So I'll go to my calculator then. I'm going to clear this guy out, and I'm going to put in the original function. So whatever this horrible derivative is, type that one in. Not what you might have done to simplify it, but what it was, totally untouched. Okay, so there's my guy. I'll do a second table. Well, that's been set up like this for ages, but you know, as long as the ask is there. And then I'll do second table, and I'll get rid of these guys. And although I don't need to do it, I'm actually going to do all of them. 2.5, 3, x at 3.5, 4, and finally 5. And the answers that I got are, let's check it out. 4.5, 0, negative 1.5, 0, and 12. Are you comfortable about how you can use your calculator to get the value of the derivative at these? These are essentially test points. And what do I mean by the sign? I mean this. Positive, 0, negative, 0, positive. And that's stage 2 done its job. Step 2. Step 3 now. Use your table of signs to find the values of x where the function is increasing or decreasing. You don't need this line, but for me, I like it because it visually helps me. There's 3, there's 4, there's 3.5, there's 2.5, there's 5. Here, the derivative is 0. Here, the derivative is 0. At 4.5, the answer is positive. Between here and here, the answer is negative. And over here, the answer is positive. And then we do a kind of logical conclusion. This guy here is positive. The conclusion I'm going to make is that everybody else is also positive. And you might say, well, how can you do it when you've only picked 1 point? Here's my argument. If somewhere over here, the answer became negative again, the only way to going from a negative, decreasing to a positive increasing, don't you need to have a zero derivative? Doesn't it have to go up and then come down? Now, there are no more up and down, so I know that that goes on forever. This guy in the middle, if one guy, in this case, this guy is negative, and then over here, all the pluses. I've got my answer here. It's increasing when the derivative is positive. Isn't the derivative positive from negative infinity up to 3? You don't count it. Where else is this function positive? What values of x is this function positive?
4 to positive infinity.
And there you go. And won't this function be decreasing, right? So this is true because the derivative is like positive. And isn't it decreasing when the derivative is negative? And in this case, isn't it decreasing from what, 3 to 4? And we're finished. Does this 1, 2, 3 process have a kind of logic to it? Does it kind of make sense? You do the critical numbers first. You build this thing I call the table of signs. You use your calculator to get as much of the work done for you. From there, you can either draw this line or not. It's up to you. You can get it from here if you want to. But from here, we can then decide it's positive, negative infinity to 3. It's positive from x equals 4 to infinity. And the derivative, because these are the derivatives, it's negative from 3 to 4. Any questions about that before I try another one? Feel good? Next question is question 7. The function is 5x to the 4. Take away 20x cubed plus 9. And we're being asked to find the intervals where it's increasing and the intervals where it is decreasing. Right. And just before I move on to that, I want to show you a little bonus that you get from this line. If you look at x equals 3, the derivative is 0. Doesn't that make it horizontal? On this side, it's positive. Positive line slope up. On this side, it's negative. Can't you now see that there's a local maximum at x equals 3? So I have a local maximum at x equals 3. Well, let's look at the other critical number, right? X equals 4, right? At x equals 4, the derivative is 0. That means the tangent line would be horizontal. On this side, it is negative, and on this side, it is positive. So what can you tell me about the shape at x equals 4? What do we call that kind of happy face shape? What's going on here?
Local minimum.
Local minimum. So do you see that table of signs doesn't just tell you when it's increasing and decreasing, right? But doesn't it also, as an extra little bonus, tell you what's happening, right? Local min, local max. Okay, on to this one now. So I'm going to differentiate and I'm going to find critical numbers. So if I differentiate this function, power rule, 20x cubed, take away 60x squared. Critical numbers then, when is this thing going to be 0? Okay. Any suggestions about making this a little bit easier to solve? Look at this expression. Anything you could do to it?
If I
That would,
out 20x or 20x squared,
I would do that. If you pull out 20x squared, don't you get x minus 3? Now, how many critical numbers are here? Well, I see 2. Would you agree that x equals 0? And the other one is that x equals 3. We found our critical numbers. That's what I call step 1, right? Done. Now I'm going to sit on my little table of signs. So 1, 2, 3. I'll need 5 again. 1, 2, 3, 4, 5. And I'm going to be putting 0 here. Right, space, 0, space, 3, space. Right? Okay, you tell me, what kind of number, what kind of test point for x should I put in this box? Okay, what number should go where my finger is?
One.
Okay, -1, I'm assuming. -2. Can you put -0.12345? Would you also agree that would be a pretty dumb one to pick? Because you want to make your life easy, so you pick numbers that are relatively nice. Okay, what about the number that goes here? Well, it has to be any number you like between 0 and 3. Could I put 1.5? Of course I could, but I'm lazy. I'm picking 2. Why? Because 2 is easier to calculate, right, than 1.5. I just want nicer numbers. Okay, what number should go at the last one, the one that's here? Think of, it's in order. What should go where my finger is at the end? Plenty of choices. Pick one.
4.
Why not? Or 10 or 22, but anything will do. And then I'm putting in the derivative, and then I'm putting in the sign. So calculator takes over. The guy I'm going to do is the untouched one. So it's 20x cubed, subtract 60x squared. I don't need table set up, so I'll go straight to table, clear out my old answers, and put in -1, 0, 2, 3, and 4. And the answers I get are -80, 0, -80, 0, positive 320. And that becomes a negative, a 0, a negative, a 0, and a positive. And I like to draw this little guy. So here I'm going to have 0. And then here I'm going to have 3. And I have 0, a negative answer. Here I have 0, a negative answer. And here I have plus. And I just fill in with a lot more pluses because I think it's helpful. So I should be able to find when it's increasing, at the values of x where it's increasing, and where it is decreasing. Would you agree that it's increasing from 3 onwards? Right. Any value starting at 3 and going to the right. So that is 3 onwards. Now there's something weird going on here. This is not a mistake. This is happening. It's negative, then it's 0, then it continues being negative. The correct answer to this is negative infinity, right? X is negative infinity to x is 0, and then from 0 to 3. why didn't I write just the whole thing in one go? Why did I write this instead of just saying, well, the whole thing's negative, right? So negative means decreasing. Can you see why I had to split it into two pieces like that?
I haven't graphed it, but I'm guessing it's just kind of a plateau.
Yeah, horizontal. You can only decrease if your derivative is negative. If your derivative is a number like 0, you're not decreasing. You're just plateauing, as Rachel says, right? You're being horizontal. So bear that in mind when you do these. Now, since I've got this picture, let's focus on what's happening at x equals 3. Well, it's negative, so it was sloping down, right? It's decreasing. Horizontal at 3, and then positive, it was increasing. And that tells me then that at this point here, we have a local minimum. Now let's look at this weird shape. It's negative, and then it's 0, and then it's negative again. See that funny shape? It kind of plateaus, but keeps going. It's like going downhill, but there's a little parking space for a second before you go back downhill again. Does anybody know what the name of this shape is? This is called the local max. There's a local max. There's a local min, right? Does anybody know what funny name this shape is called? Okay, here goes. Try and remember it, because you may have to use it sometimes. Don't think you've ever been told it yet. It's called a horizontal point of inflection. Wow, weird mouthful, right? But that's what it's called. Horizontal point of inflection.
Does that matter whether it comes from decreasing or increasing?
Yep. So you can have a horizontal point of inflection looks like this, and you can have another horizontal point of inflection like that. They're both called horizontal points of inflection. In fact, we know a curve that does that. Does an x cubed do that? You know, so they're not that uncommon, right? You will see them from time to time. Are we feeling good? Now you've seen two, there's a kind of theme. So let's make life hard for you by picking a derivative that's ugly. Straight into question 8. We are going to find when is that function increasing, when is it decreasing, and we're also going to find any local max and mins or points of inflection that it may have. What technique do I do or will I use to differentiate this guy?
Product rule?
Yeah. So I'm going to call this guy F, going to call this guy G. And I'll give you a little warning here. You are not going to like the algebra that's going to come out of this question. It is downright ugly. Well, if you differentiate this fractional power, you multiply by the power and reduce it by 1. And then you leave this guy alone. And then you add, you leave this guy alone. And then you multiply by the derivative of this, which is 1. And so I have 2/3 x to the negative 1/3, right? X take away 6 plus x to the 2/3. So far, so good. Now, I promised you that this one is going to be really ugly, and it is, because I'm going to have to do style points on this, and it's just not nice. No two ways about it. First thing I'm going to do, so I want to take it as slow as I can, is I'm going to make that negative power go on the bottom. Are you comfortable with that guy became this guy? Right? Now, I have an ugly fraction plus something that ain't a fraction. I want to add these together. I want to combine them into a single fraction, because in this type of question, you need it to be together, right? You need it to be a single fraction. And so what I'm going to do is I'm going to multiply this guy by 3x to the third, top and bottom. That's a special version of 1. Why 3x to the third? Because this guy is 3x to the third. Let's see what we get now. We get 2 lots of x minus 6 over 3 lots x to the third plus. If you multiply these two together, you get 3x. Now, check it out. X to the 2/3 times x to the 1/3. Well, you add 2/3 to 1/3 and you get 3/3, which is 1. So you get x to the 1. And it's also over 3 lots of x to the third. So now, since they share a common denominator, I have this guy. You still with me? Horrible as it is. What do you think I'm going to do to this top expression? 2 lots of x minus 6 plus 3x. What do you think I'm going to do to that? It's the most obvious thing to do to it.
Multiply that and then combine like terms.
That's what I would do. And after all that hard work, and damn it, it was a lot of hard work. Do you know what? The only thing we've managed to do is write down the prettiest version of the derivative we can. So over here, the derivative of this function is 5x take away 12 all over 3 times x to the third, which I'm going to rewrite as the cube root of x. Okay. Now I'm ready to find critical numbers. Let's go hunting for when is this function undefined, because they are critical numbers. You don't need to do a lot of work now. If you look at this fraction, aren't you going to have undefined when the bottom is 0? And would you agree that x equals 0 makes the bottom 0? So x equals 0 is one of my critical numbers. Now the other kind of critical number you get is when the derivative is 0. So I need to make or find the value of x that makes this ugly thing 0. The good news is that when you are dealing with a fraction and it's equal to 0, all that matters is that the top needs to be 0. So you can pretty much ignore the bottom. And so I have 5x take away 12 is 0. Add 12 to both sides and then divide to get that. And so here are my 2 critical numbers. Would you agree that's a lot more work than a polynomial, right? Polynomials tend to be pretty easy to do. That guy there, no. So that's step 1 done. So I'm going to do x and f dashed of x and the sign. And the numbers are 0 and 12/5. So something, 0, something, 12/5, something. Okay. Any number over here will do. Number I'm going to pick is -1 because I want to. That's roughly, what's that roughly? 2.4, right? That's 2.4. So give me a number that would fit in here. Something between 0 and 2.4. Give me a number.
1.
1. Okay. Always think easy. Right. Give me a number that's bigger than 2.4, but make your life easy.
4.
Okay, 4 will do. 3 and 5 will do, whatever you want, right? That'll work. Now, this bit is going to come from our calculator. So, and quit. There's the derivative, so I'm going to have to type that in. That's probably going to be a bit messy. But here goes a bracket. 5x subtract 12 divided by, I'll need another bracket, 3 times the cube root of x. I could go hunting for it, but I'm not going to. I'm just going to call it x to the power of 1/3. So that's how I got the cube root of x. So you type the derivative into the calculator, and then we go to the table, rub out the previous answers, and put in -1, 0, 1. Oh God, 12/5. Okay, 12/5, that'll work. And 4. And the numbers I got are what I'm doing with my colors here. 5 point, I don't even care the rest. 5.6. Error, well, that's because it's undefined. And then I got -2.3, and then I got 0, and then I finally got 1.6. And now I can put in what the signs are. And in this case, the signs are going to be 5.6 is positive. That's undefined. This is negative. This is 0. And this is positive. And then I'll draw my little line. And I'm going to put here at 0 and here at 12/5. And on this guy, it's 0. And here it's undefined. And what do I have? I have here is positives. In the middle, it's negatives. And here is positives. Right. I should be able to get increasing. Increasing is when it's positive. So it's positive, anything less, x less than 0. And it's positive for any value of x bigger than 12/5. And it's decreasing when the derivative is negative. And that's from values of x from 0 to 12/5. Do you notice when I draw this number line, I only put in the critical numbers. And the reason I only put those guys in, if I put a little mark here with -1 and then 1 here with 1 and 1 over here with 4, those other numbers, I sometimes accidentally put them in the intervals. Have you noticed that the intervals only start and finish at critical numbers? Right? So if you only put critical numbers on this little line at the bottom, do you see how you're less likely to put in a -1 or a 4 or something by mistake? So if you're wondering why I do that. Now, interpreting this is going to be a bit tricky. Negative, coming down, horizontal, positive. Oh, well, that one's not. That's a local min. I'm happy with that one. No. This one is positive. Don't know what's happening. Negative. That's weird. I can't say that this is a local max or a local min. It could be. Couldn't it be because it was a cusp? You know, one of those things. But it could happen because there was a vertical asymptote. So if you're saying, well, how do I know what? Can't you just plug it into your Desmos and look at it? And you'll be able to tell what is happening here. In fact, all the stuff that I've been doing you should be able to go back and look at it in Desmos and say, yep, it's increasing to 0, and then it's decreasing, and then it's increasing somewhere else. So we've got time. Yeah, we have time. I'm going to open up Desmos, and we're going to look at this one, the one we've just finished doing, which was originally written down like this, right? And we're going to see if it matches everything that we've decided, right? So let's jump over and see what we get. So it's going to be y equals, it's x to the 2/3. So that's x to the power of 2 divided by 3. Okay, that works. Brackets, x take away 6, close brackets. Wow. Oh, I just noticed something I typed in wrong. There we go. Oh, now, is this function increasing from minus infinity up to x equals 0? Agree, it's going uphill just like we said it was. Does it go downhill from here to there? I bet you that's 12/5. Can you see it? 2.4 is 12/5. And then it's got a local minimum there. Yep, we said that. And then isn't it increasing forever? Do you see at the origin, the one I wasn't sure? Can you see it sloping down, sloping down? And isn't that funny little guy there one of those things that's called a cusp, right? A corner. Everything that we've done here exactly matched that picture. I do not want you, and I'll say this again, I do not want you to say, I don't like doing all that horrible math. I'm just going to draw the picture and figure out what the answers are. And the couple of reasons for why I don't want you to do it that way. I don't mind you using it as a check. I think that's a great idea. You know, just draw it and make sure it works. You know, check it. Is that not all critical numbers are nice numbers? Can you imagine that one of the critical numbers might be at x equals the square root of 3, right? If you use Desmos, Desmos doesn't tell you square root of 3s, doesn't it tell you 1.5677998 or something, right? So you won't be able to tell me the exact value. WebAssign is expecting the square root of 3, so you'll get that one wrong. And when you're doing tests, I will make sure that I give you questions where they're not all nice numbers to make sure that you're not cheating. And I call that cheating. Technically, I guess you're answering the question, but you're not answering it the way I want you to do it. And the last reason is, it's much better if you can get an understanding of what calculus is telling you about a curve, so that then you can feel really comfortable with saying, well, I don't always have the time to do this, but I can go in Desmos and look at it. But I know that if I really had to, I could prove it from scratch. So the analogy would be, I know how to multiply a 5-digit number by a 4-digit number by hand. I know how to do that. I use my calculator, but I'm comfortable with doing that because I know how to do it by hand. Can you imagine if you didn't have this? You would just be saying, well, you type things into this machine and you look at the picture and you write down what you see. You see, you don't really know why it is what it is or how it could be done any other way, right? So you've got a deeper insight into, why is that a funny corner? You know, why is that okay? But why did this go funny? Well, it went funny because the derivative was undefined. And we know undefined tends to make weird things happen. So I can understand why that's the case. So I hope I sold you that you really do want to do these guys the old-fashioned way. And then, you know, in the future, yeah, use a calculator. Last question for today is going to be question 9. And the function is this one. Now, I have to do this one a little bit in the quick side, but here it goes. Would you agree this is a quotient rule? Right, to find its derivative, I need to do a quotient rule. So the top is going to be called f, the bottom is going to be called g, and so the derivative function is f dash g, take away f of g dashed, all over, whoops, almost put the answer in there, all over g squared. So if you differentiate this guy, you get 2x, and you leave this guy alone. Subtract. F left alone, derivative of that is 1. The whole thing is over x minus 4 squared. I'll distribute this now. I get 2x squared, take away 8x, take away an x squared. Combine the x's. Can anybody tell me a little bit more work to do? I want style points on this guy. What could I do to the top? The numerator.
Factor
Agreed?
x minus
Right.
4.
Yeah.
And x plus 4.
Oh, not that factor. That would be for a difference of 2 squares. I'm just going to factor out an x. You notice they both have x's, right? You were thinking of a difference of 2 squares, I'm pretty sure. Right, for this guy here, there are 3 critical numbers, right? 3. Tell me, oops, well, I've just told you one of them, 0. Tell me any of the other 2.
8 and 4.
Are you all comfortable about critical numbers? Where derivatives are 0 and where derivatives are undefined. The 2 at the top give me x equals 0 and x equals 8. And that guy in the bottom, that's going to give me a critical number because it's undefined at x equals 4. Table of signs coming up. My x, my derivative, and my sign. Now, in numerical order, right, we've got a 0. So something 0, something 4, something 8, something. Are you happy about how I set up my table with 0, 4, and 8? Right, I need to pick guys. This guy, I'm going to pick -1 because I want to. This one, somewhere between 0 and 4. Some guy between 4 and 8. And I felt like putting 10 at the end. Are you comfortable about how I chose the in-between values? Right? Any number between 0 and 4, critical number. Anyone between these two. Anything after 8, anything before 0. Then I'll go back here. And you're getting a kind of quick version because we're kind of running very short of time here. Bracket x squared. Oops, wrong guy. It's this guy down here. It's derivative I should be putting in. So it's x bracket, x take away 8. Close the brackets. Divided by x take away 4 squared. Yeah, that looks good. I'll do second table now. Clear out the last answers and put in -1, 0, 2, 4, 6, 8, and finally 10. And we get 0.36. Don't really care about the rest. 0, -3, undefined. That's what error means. -3, 0, and about 0.5. So we are looking at 0, undefined, 0, and then it goes positive, negative, negative, positive. Draw my little number line. Only put in the critical numbers. And I just, yeah, there's we go. And at the critical numbers, I've got 0 here, I have an undefined here, and I have a 0 here. And this guy's positive, this is negative, this is still negative, this is positive. I like to fill in with a few extra negatives, or a few extra positives. So I should be able to tell the values of x where it's increasing and the value of x's where it's decreasing. Positive derivatives. Anything less than 0 is increasing. Anything bigger than 8 is increasing. You happy about those two guys? Okay, what about the decreasing? Right? Negative derivatives. Now you see that little undefined guy? He breaks us into 2 different distinct regions.
Oh,
So what you're going to have is from 0 to 4, and then from 4 to 8. Are we comfortable about that interval? Anything less than 0, anything bigger than 8 is increasing. From 0 to 4, little pause, from 4 to 8. If I was wanting, and then very often you do, at 0, it's positive, sloping up, right, increasing. So isn't there a local max at 0? What's happening over at x equals 8? Well, it's negative doing that, 0 doing that, positive doing that. So wouldn't you call that a local minimum? And would you agree something weird is happening here? But it looks like it's coming down, undefined, and coming down. If you check on the calculator, this one is not a cusp, right? It's not a little hill with that. In fact, it's a vertical asymptote. So nothing is happening at 4 that has an A. Rachel. I can't hear you, Rachel. You have to hit space bar.
Oh, I was just looking at what the shape would be like. It looks like it's a discontinuity. I can't remember the name, but
It's
yeah.
vertical discontinuity.
Okay.
And that's a vertical asymptote from 141. Right? You know, one of those, it's like a volcano one. This one is one of those, it goes up and then it comes down on the other side. So it swings up this side and it swings down, but it's a vertical asymptote. And you can check it on your calculator. I just
Okay.
don't have time for it. Okay, last name, and bye-bye, guys. And just to remind you, in case you came late, this section is now not part of your homework for this week. It will be part of your homework for next week, because on Monday, hopefully, we'll get the rest of this finished.
Thank you.
You're welcome. Have a great weekend, guys. I'll see you Monday.
I got a quick question for you.
What you got?
I was doing my homework and the WebAssign kind of disagreed with some of the answers on the question 1 and 2 that you went over the day or two ago. It's in the maximum and minimum values.
Okay. Now you put in the x coordinates, which is what they want. So let me have a look. Yeah, let me have a look at your question, your specific ones here.
Oh boy, I don't have WebAssign up.
I have it here. Okay. So are we talking 4-1 max and min? Is that the question?
Exactly.
Okay, so right. So yeah, max and min. Well, you got question 1 right. So I guess I should move to 2. Right. Yeah, we did disagree, and I remember going over that in class, and I understand why they picked what they picked, but I don't agree with it. So the answer to local maximum in this question, there's a local maximum at R. Right. I'll show you the picture, because since you don't have it in front of you.
Because originally I did put R down as well,
and it didn't agree with you, right?
Then no, it didn't. So then I changed it.
Yeah, I understand why you would do that, because normally that's what you should do, right? Because it's not the answer. Right, when you can see their answers there, they do have R and they have B, and I'm arguing about B. B is not, well, if you look at that dot, there is an argument that that dot counts as a local maximum. I don't think half of you will
What do you have a jump? So when you have like a jump discontinuity?
Yeah, don't use it. Is my advice. WebAssign says do use it, and I'm saying don't. There are some disagreement about. It's not WebAssign. There are mathematicians who will say to you that a local maximum doesn't need to have a hill in it, and there are others like me who say you do need a hill. Right? If you want to be a local maximum, you have to go up and then down. They're saying you only need to go up. Right? So you'll have to argue with the math world because we haven't agreed between us which one of those is the correct one. So all you're going to do is write down the answer that they've got so you can get the points. All right. Thankfully, there are only a couple of questions like that where there's maybe a disagreement. Now, if you do neither a maximum or a minimum, the answer that they're picking is only S. Or I should say it's C and S. Now, you picked S, which is correct. And they're going to allow C, and I'm not going to allow C. And so if you were doing an exam question, you would go my way. But to get the points, just call it C, S, and you'll be fine. So what they're doing is that they're allowing jump discontinuities to be local max and mins or to be not max and mins. And that is causing us a great deal of grief. But once I take over the world, I'm going to fix that. I'm just going to tell all the mathematicians I'm right and you're wrong. By the way, it's not just me. I'm the only guy who says this. Right? If you asked half the math professors at OC, they would agree with me. Of course, if you asked the other half, they would totally disagree with me because it's one of those. As long as you define what you mean, then it's correct. And I define a local max as a hill, right?
Yeah.
They define a local, the other group say a local max is you get up to here, right? It's locally, it's a hill. Well, it's not local. It's locally, it's a top of something, right?
Yeah.
And so if you want to define it that way, that's fine. In which case you will answer it the way they did. But if you want to define it as a hill, right, the top of a hill, then you won't use what they think is the answer, right? You'll use maybe a slightly different correct. So I've ranted on there. I think I'm trying to say we're both correct as long as you know how we're defining what a local max means.
Yeah. Gotcha. All right, thank you.
Yeah, and my brain, yeah.
So you can have both, you can have more than one local maximum or minimum.
Two, yeah, you could. Remember the sine function? That one? Doesn't that have an infinite number of them? And if you have a fixed start and finish, yeah, there's only a finite number, but you could have 2 or 3 within an interval, couldn't you? And aren't you also allowed to be an absolute max and a local max at the same time? Right? Some things can be both. Not all of them, but some of them can be both. Because you can get some that are just local max, and you can get others that are local and absolute max, right? Are we good?